All right. Good afternoon, class. Let's get started. So today is Friday, so I'm gonna check your attendance. Before checking the attendance, let's see the survey session. One student requested to include some illustrations showing the fork functions. So I prepared it. So if you see these figures, I think it would be better to understand the flow of this C code example. So this is the parent process, and this one is the created child process. So when we use the fork function, child process is generated. However, the generated child process will start from this line. So even if we have the exact same code section, but this code will not be executed. So this and this strings will be printed. And here's one other example. So we have parent process, and so it will create one child process, two child process, and this child process again will create a child grandchild process. Okay, so yeah, if you see these figures, I think you can understand that. And before checking attendance, I want to I prepared some quiz problems to understand the fork functions and wait function. So can you guess how many times A and B would be printed? I gonna include these kinds of problems in your keys and final exams. So how many times are A and B printed? Any volunteers to answer the times? Oh, yeah, thanks. Yeah, correct. Yeah. A will be printed 2 times and B will be printed 3 times. So let's see this figures. So here's the parent process, and firstly the fork function is called, and so the return value of the fork function for the parent process, it will receive the PID, process identifier of the its child process. So at here, this fork function will return some PID of this child process. So maybe let's say its PID is 1, 2, 3. So for the parent process, these codes will not be executed. So at this process, only one B will be printed. And for the first child process, so for the child process, the fork function will return 0, right? So these code will be executed. So for this child process, 1A and 1B will be printed. And again, from the first child process, the second child process will be created. And at here, its PC is pointing this, right? So the second child process will be start from here. So the second child process will result out 1A and 1B. So finally we will receive 3 B's and 2 A's. Yeah, so the answer was 3 and 2 and 3 times respectively. I also prepared one more quiz for which is related to the weight function, but we were gonna solve this problem after the attendance quiz. By the way, you can still solve this quiz problem during the attendance check. For your information, I guess I remember that in the previous slide, I just wrote down a weight function like this. However, weight, null, and just weight, their functionalities are identical. So, yeah, you don't have to care about this null value. Okay, then let me check your attendance. Suba, 윤민성, Mo, Tikinas, Lucas, 조윤솔, 이수민, 레오, 실파, 오렐리, 김민성, 표, 노연우, 윤아라, 이강민, 완, 한채영, 루슬란, 베네딕트, 안현식, 아무리나, 차승호, 조은재, 이동훈, 네이선, 하미마, 정준희, 이재준, 김동현, 둔, 이민훈, 송민혁, 강희진, 손아현, 김예원, 박승빈, 최지원, 나미, 찬, 김다희, 김민채, 강한결, 전영재, 이주호, 알반, 방채진, 박희현, 강민수, 슈디, 김현중. Did I miss anyone? Yeah. Anyone else? 실바. Okay. So, what was the possible output of this program? There is only one possible output for this program. We have one weight function and one fork function. So let's see this figures. So this is a parent process, and it will create one child process. And at this PID variable, so for the parent process, it will save some PID of the child process, and 0 will be saved in PID of the child process. So parent process will execute these lines, not this line, and child process will execute these lines, not this line. So let's say let's consider the two cases. So for the first case, let's say that after this fork function, the parent process is running first. And for the second case, let's say that after this fork function, child process is running ahead of the parent process. So let's firstly see this first case. So after the fork function, even if the child process is created, these lines will be executed. And at here, the parent process will face this wait function. And due to this wait function, parent process will wait for the termination of the child process. So after this code, the child process will be executed. So the PID of the child process is 0, so A will be printed firstly, and then C will be printed. So the A and C will be printed. And after the termination of the child process, we can resolve this wait function. So after that, the B will be printed, and then C will be printed. So the possible output of these two processes is AC and BC. And then let's take the second case. So after the fork function, let's say that the child process is executed ahead of the parent process. Then likewise, A will be printed firstly, and then C will be printed. So A and C will be printed. And after the termination of the child process, the parent process will be executed. So it will not be printed. And then B and C will be printed. And even if there is a timer interrupt occurred, so let's say after printing A, the context switch is occurred. So we go back to the let's say we go back to the parent process, and even if there is a timer interrupt and the context switching, eventually the parent process will encounter this wait function. So the result will also be AC and BC. Yeah. So far, any questions? You can ask in Korean and also in English.
Parent process fork 2 or 3 times.
Mm-hmm.
Then and parent process made a wait node. 그 프로세스를 여러 번 훅한 다음에
예.
그 웨이트 널 있으면은 그 자식 프로세스가 전부 다 종료될 때까지 기다리는 건가요?
아, 아니요. 그 여러 개 프로세스 중에서 그 차일드 프로세스 중에서 하나만 기다립니다. 그러니까 아무거나 하나가 끝나면은 웨이트가 끝납니다. So I will show you some materials. So the question was, if the parent process use the multiple fork functions, then how does the wait function work? The question was that. So yeah, when fork function is called multiple times, then this wait function will only wait any one child process to be terminated. So yeah, does that answer your question? Okay. Yeah. Okay. As I described here, these kinds of problems will be included in the quiz and the final exams. Okay. So from the last class, we ended up class by explaining this process termination, and I have told you that we were gonna see some example C codes of the zombie process and orphan process. So the zombie process and orphan process. So for zombie process means child is already terminated and parent process is alive. For the orphan process means child process is still running, alive, but parent process is dead, terminated. So zombie process means this dead child process, and orphan process is meaning this alive child process. In this situation, the child process is waiting for wait function, and the program is terminated. However, their informations are not deleted from the memory. There's the code sections, data sections, or those things will be disassembled from memory. However, their PID and some process table entry information will be remained until it meets the wait function. So the zombie process is problematic. They are the problems. However, orphan process is not. They are unproblematic. So the orphan process do not harm the system. However, because zombie process they still occupy a process table entries, and they also occupy the process ID. So the zombie processes are problematic. So if we have too many numbers of zombie processes, then creating new processes can be very difficult or impossible, because there are limited numbers of PIDs, and if the zombie processes they occupy the PID, then we cannot generate new processes. So zombie process is problematic, and orphan is unproblematic. And in case of the ORPAN process, when the parent process is dead, then the ORPAN process's parent process will become some some kind of corner process. So they will be adopted by some init or systemd process. So I prepared two zombie and ORPAN process code. Let's see this one, the zombie process. Okay, so firstly, parent process will call a fork function to create a child process, and because parent process is sleeping, so during the sleeping of the parent process, the child process will be executed. So print this thing, and the child process will be terminated during the parent process sleeping. And yeah, I prepare the flow of the process creation and the code. So the child process will be created, and during this sleeping for 10 seconds, child process will be terminated. And during this 10 seconds, this child process will become a zombie process, because because child is dead but parent is alive. So this flow will create a zombie process. And today we're gonna see a live demonstration to how this works. And here's an example C code for the ORPAN process. So likewise, we will create the child process by a fork function, and child process will sleep 10 seconds, and parent process will immediately terminate it. So during the child process's 10 seconds sleeping, parent process will be terminated. So during the child process's sleeping, parent process is terminated. So during this 10 seconds, this child process doesn't have its child process. So it will be adopted by some init or a systemd, which is kernel processes. Yeah. And yeah, we're gonna see a live demonstration to understand this zombie and ORPAN processes. And to understand and follow the live demonstration, you have to understand some commands to handle the processes in your shell terminal. So we already know the Control C, right? Terminating the current process. And you can use Control Z to pause the current process. And after this pausing, we can resume the paused processes by typing BG or FG. So BG will resume it in background, and FG will resume the paused process in the foreground. And we can use PS command to show some processes in the current terminal, and we can add -L option to see the PID and the parent PID, PPID. And when we typed this PS-L, we can check which process is a zombie process by checking this letter Z. Then I will show you this live demonstration. So I have already typed it or the C codes, and I also compiled them. So let's see the 준비 process firstly. So when we run the 준비 code, then the child process and parent process will print each strings, and after 10 seconds, parent now I exit will be printed. Only seeing this, we cannot understand what is the 준비 process. However, by pausing the process, we can check the 준비 process. So after running this program, let's press Ctrl Z. Then the two processes will be stopped, and we can type by typing this PS. We can see these two processes are exist in this terminal. And by typing PS -L, we can see that the PID and PPID of the two processes. So the PID of the parent's 준비 process is 1422, and the child process's PID is 1423. So when we check the PPID, the parent PID, the child process's PPID is the parent process's PID. And when we check this Z letter, we can see that the child process is a 준비 process. This letter Z indicates this process is a 준비 process. So which means that the child process is already terminated, but because and it is waiting for the parent process wait function. Yeah, and by typing FG or BG, we can listen the pause process. However, when I type this FG command, then immediately this string will be printed, because this sleep timer is working independent of this pausing. So when I type the FG, then because the 10 seconds is already passed, so the last string will be printed immediately. So it is the example of the 준비 process. And let's see the orpan process. So unlike the 준비 process, the orpan in this orpan example, the parent process will be exit first. Yeah, and in the background, the child process is sleeping. So after 10 seconds, child process will print this one. Yeah, now it is printed. So after 10 seconds, we can see that the child process is printing. And then let's type the PS and PSL after running this orpan. So when you see this orpan, so the parent process is already terminated. So we cannot find the parent process when we type this PS-L. However, we can see the alive child process, and when you see the PID, then the child process PID is 2393, and I guess the PID of the parent process was 2392. However, because the parent process is already dead, so the child process lost its parent process, and it is adopted to the higher levels corner process, which number is very small. So we can see that the PPID of the orpan process, the child process, is changed to the system D or init process. Okay, that's all for the orpan process and 준비 process. Any questions so far? Yeah. And I prepared 3 quizzes to guess the zombie, orphan, or neither. So, could you guess this code will create a zombie process, or orphan process, or neither? I prepared 3 quizzes. I give you about 3 minutes to guess the answers. And for your information, I didn't make a trap for this string, so you can trust this string's meaning. And one more for your information. So for the third quiz, I just added this one line from the zombie process example. So I just add one wait function at here for the third quiz. Alright, so the answer was orphan, neither, and neither. And then let's see the live demonstration to check the answer. Okay, so we have quiz 1 code, and let's run this. So the answer was orphan, right? So when we run this code, parent process will be finished early, and child is still running. So when we type this ps-l, then we can see the quiz 1 is still alive, and PPID is changed. So the quiz 1 will generate open process. And let's see the second quiz. So when you run the quiz 2 code, then parent will wait for the child process to be terminated, and after the child process exit, then directly parent process will be will be terminated. So when we check the PSI panel, or when you stop the code, and even if after checking this one, then we can see that child process, parent process is the PID of the parent process, and we cannot find any Z. So the quiz 2 will not generate open process nor zombie process. And also the third quiz code will not generate the zombie nor open processes. So yeah, after the termination, we can not find any open or zombie processes. And even if we pause the program and check the PSI panel, then there is no zombie process. Oh, I think okay, for the third quiz I will check the later. So I have thought that quiz 3 will not generate the open process. However, when you see this PPID, then it means this PPID is smaller than the PID of the current process, right? Then it means the child process is open. So okay, I will check the third quiz again, and I will explain you in the next class. Okay, so that's all for the process management, and from today we're gonna learn about the thread management. So what is a thread? Thread is a flow of execution with its one execution state. So thread is very similar with the process. However, thread is a smaller one. It's a smaller concept. So it's a small unit of execution. So it is a basic unit of CPU utilization. So as I told you, thread is very similar with the process. However, thread will be included in the processes. So process can generate some threads, and the thread shares the same processes, code section, data section, and the processes OS resources such as the opened files. And threads within the same processes can share the resources such as code, data, heap sections. So threads within the same process, they will share the global variables. So heap stores the global variables, right? And data section. However, each thread has its own stack. So local variables will be stored in they are stored in the stack, right? So local variables will not be shared among the threads within the same processes. So you may have heard about the thread, right? We use the thread to use some multiple CPU cores or for the parallelism. And there is one more reason to use the thread. So in terms of context switching, there is some strength for using the threads. So threads share the same processes, code section, data section, and some memory spaces, right? So for the context switching, the threads, the context switching among the threads within the same processes, it is much more faster. They will be cheaper than the context switching among processes, because threads share the code section, data section, and heap, or blah blah blah. We don't have to change, or we don't have to do some things to handle them during the context switching. So the thread context switching will be cheaper than the process context switching. Yeah, that is one more advantage to use the thread. So the traditional computers, the old computers, has implied that a process is a program. So one program is a one process. However, so it is said a single thread of execution, and also called single threaded. So this single thread of will control the process to perform everything. However, most modern operating system provides features multiple threads of execution. So one program can have multiple threads. So each thread can performed in parallel. So we can enhance the performance of the program by using the multiple threads in one program. And yeah, most modern software applications are multi-threaded. So multiple tasks within the application can be implemented by separate threads. So here's an example, multi-threaded server architecture. So we have client and server, and when client sends a request to a server, then the server will not handle the request, and instead it will just create a new thread to handle this request. So this request will be handled by this new thread, and the server will listen to listening the additional client request. So without this multi-threading, the server has to handle this request. So if we cannot use the multiple threading, then server have to handle this request. And during this request handling, server cannot listen a new request from other client, right? Then other clients have to wait the server, and it is not very responsible. It is not good. So we have to use this multi-threaded programming for the server architecture. And most operating kernels are also multi-threaded. So during the system boot on Linux systems, several kernel threads will be created. And we have one special kernel thread, which is called kthread-d, and its PID is always 2. So this kthread-d will serve as the parent of all the kernel level threads. So we have the special kthread-d process, and it's the parent of all the kernel level threads. So every time a thread is needed to be created in a kernel memory space, this kthread-d will be invoked. So when you create the when you want to create a thread in the kernel space, you have to use this kthread-d. So it is because in a user space system core, you cannot create a kernel thread because it's a user space and you don't have some permissions or privilege to handle the kernel space. So through this kthread-d, the kernel threads will be created. So when you type this command on your Linux system, you can see these kinds of results, and you can see the PID of the kthread-d is 2, and it doesn't have its PPID is 0, which means it doesn't have any parents. So there is some very limited numbers of special processes which doesn't have parents. One another example is systemd and or init process. They also doesn't have the parent process. And here's the kernel threads, and you can see the PPID of these kernel threads are always 2. So k thread d is the parent of the all of the kernel level threads. And I just prepared some supplement to understand this command. And instead of this command, you can use this command to check the thread trees. And however, you cannot see the k-thread d in the WSL because they use different kernels, so you cannot check the k-thread d in WSL. So to check the k-thread d, you have to use the vanilla Linux machine or virtual machines. And here's benefits of multi-threaded programming. So because the threading allows continuous execution of the processes, so it serves responsiveness, and you can share some resources among the among the threads. So because they share the heap sections, data sections, and code sections. So by using threads, you can save some memory spaces, and it offers economy because, as I told you before, context switching among the threads is cheaper than that of the process ones because they share some resources. So they offer economy, and so a process can take advantage of multi-process architectures by generating multiple threads. So we can get scalability by using the multi-threaded programming. However, using a thread is not easy. So using thread will occur some issues. So we're gonna see this synchronization issue. So in multi-threaded programming, several threads which are quietly possibly sharing data should be well coordinated. So otherwise, the threads access can outcomes the execution of the particular orders. And okay, I'll show you this lace condition. So so this is an example of the lace condition. Let's say we have 2 threads, and these 2 threads share the variable x. Let's say this x is a global variable. So x will be shared among all the threads. And let's say the thread A read x and write x as 1. And let's say thread B write x as 2. And if the thread B writes x equals 2 after thread A writes x equals 1, then thread A's update will be overwritten, right? So after this instruction, thread A will expect that the value of the x equals 1. However, because thread B can also access this variable x, it can change the value of x as 2. So even if thread A expects the value of x as 1, its value can be 2. That is, this situation is called race condition, and it is problematic. Yeah. So to handle this race condition, we have to use some functions, or we have to change kernel. So we can use mutex or atomic operations, which will be you will learn this stuff in the operating system calls. And so the key idea is that protecting some code or protecting some variables by using this critical section. So to handle the critical section, you have to get some permission, and in that way we can prevent this race condition. And another approach is using the non-preemptive kernel, which guarantees any process threads running in kernel mode until it exits. And I prepared to compare the preemptive scheduling and non-preemptive scheduling. So most modern operating system is using this preemptive kernel or preemptive scheduling. So operating system can interrupt the running process or thread and switch to another. So if the operating system will generate an interrupt to switch among the processes or threads. However, if we use the non-preemptive scheduling, then there is no interrupt. So the running process threads keeps the CPU utilization until its exit or until it voluntarily gives it up. So if we use this non-preemptive kernel or non-preemptive scheduling, we can prevent the race condition. So as a side note, I have released some papers related to this non-preemptive scheduling. In most cases, we have to use this preemptive scheduling. However, for some systems where responsiveness is not important, non-preemptive scheduling is effective because you don't have any context switching, so we can save some time, and it is some security issues will be also solved. So we cannot say that preemptive kernels are free from race condition. So if we use the preemptive scheduling, we will suffer from race condition. Nevertheless, why would anyone favor of preemptive kernel over a non-preemptive one? Most operating system is currently using preemptive scheduling. This is because it is more responsiveness and more suitable for real-time programming. So it can, for the interactive programming, interactive computing, we have to use the preemptive kernel. So even if we suffer from the race condition, most computers are using this preemptive kernel. And and to use the threads in user level program, we have to consider this multi-threading model. So support for threads may be provided either at user level for user thread, for kernel and by the kernel, or for the kernel. So user level programs can use the thread, and kernel programs also can use the thread. So user thread will be managed by a user level threads library, and kernel level threads will be managed by the operating system, like KThread. However, user level programs can generate or they can use the thread. However, user level threads may not be visible to the operating system. Only kernel level thread can be directly scheduled by the operating scheduler. So even if we generated a thread in the user program or user space, kernel thread will be generated. So when a user program creates a thread, then the kernel thread also will be created, corresponding schedulable thread. So because user level thread is not visible to the operating system, we will generate the kernel level thread. So the thread can be scheduled by the operating system. So there is a relationship. There is a relationship that must exist between user threads and kernel thread. Many to one means multiple user thread will create one kernel thread, and one to one means one user level thread will generate one kernel thread. And many to many models means many kernel many user threads will generate many kernel threads. So in Linux and Windows operating system, so most operating system is using this one-to-one model to handle the user level threads. And user level threads will be managed by a user level threads library. And there are many thread libraries such as POSIX, Windows threads, Java threads. And we will gonna focus on this POSIX thread, user level thread library in Linux system. And specifically, the name of the POSIX thread is pthread. So it's a POSIX standard defining an API for thread creation and synchronization. So it is just like a standard specification. It is not an implementation. So POSIX standard will offer some specifications, some spec to how to use this library. And the detailed implementation will be decided by operating system designers. So numerous operating system implement this pthread independently, and their detailed implementation methods will be varied. So yeah, that's all for the pthread. So by using this command, we can create a user level thread. And then how can you implement this thread in Linux systems? So thread creation is done through clone system call. So clone is it behaves identical to fork. However, this clone function can accept some arguments like this one. So clone function will take some flags so that dictate the resources to be shared between parent and child. So as I told you before, thread process will share some memory space like code section or heap section of its parent process, right? So by passing these flags, we can create a thread instead of process. However, if none of this flag is set when clone is invoked, the behavior of the fork function and clone function are identical. Yeah, so fork function is nothing more than a special case of a clone function. Okay, so that's all for today. Do you have any questions related to the thread management or etc.? Okay, then before ending our class, I will take a survey.
스레드를 많이 만들어줘도 CPU가 적혀 있을 의미가 없는 거예요.
그 의미가 없진 않고 컨텍스트 스위칭 할 때, 그러니까 뭐 극단적으로 코어가 하나면은 그래도 번갈아 가면서 하는데 의미는 없고요. 근데 뭐 속도가 빨라지진 않죠. 퍼포먼스 측면에서는. 네. 그거를 여기 써줄래요. 그 다음 시간에 그 영어로 설명을 해줄게요. Okay, that's all for today. Enjoy your weekend and see you next time. There will be no coding on the exam.
제가 화요일날 퀴즈 제출을 못했는데